Hi everybody, welcome back. We talked in our last video about set theory, about what's a set, what does containment mean, what does equality mean. In this video we want to talk about not just what's a set, but also what we can do with sets, in particular operations on sets. So suppose that we have two sets, A and B. The union of A and B will be a new set. And we get that union by making a new set, throwing in everything from A with everything from B. In other words, A union B is the set of all elements X, right, which are contained in A or which are contained in B. Okay? So you notice there's an or. Obviously, we're setting up places where you can see proof by cases having to happen when we start writing these proofs, right? So to prove that something's in the union, we have to prove that it's in A or that it's in B. Well, obviously, intersection is the next thing to do. The intersection of two sets would be what you get when you look at all the elements X which are in the set A and also in the set B. Okay? Again, lots of places where you can see proof by cases and things like this is going to happen because of the ands and the ors. Now you may have noticed our symbol for intersection looks like a, well, uh, I'm not sure exactly what that looks like. Kind of an N, right? Just pointed down. Our symbol for um, union was like a U. And if you think back to our symbols in logic for disjunction and conjunction, in other words, for ands and ors, those were sharp cornered V's. So the intersection and union symbols are a lot like our pointed and or symbols. Now they're just rounded off to make intersections and unions. But we get a new one when we talk about sets. We also can talk about the complement of a set. So A, then now a backslash and a B, right? That means the set of all x's which are in A but which are not in B. A lot of times people will read this as A minus B, right? So A with that backslash and then B means, well, everything in A and you throw away everything in B. So sometimes I'll call this A throw away B. Right? So we take everything in A and keep it. We take everything which is in B and we throw that away. Okay, so this needs some examples. And we need to do some more complicated sorts of proofs because this is the kind of thing you'll have fun doing in the homework. So here's a theorem. It's not very difficult, and if you let your eyes go a little blurry and stare at it, it kind of looks like a distributive law, right? And in fact, that's exactly what it is. So on the left-hand side, we have the brown set A intersected with parentheses green B union C. Okay, so this is like having an A outside of a parentheses. On the right hand side, we have A intersect B union with A intersect, did I say that right? A intersect B union with A intersect C. So it looks like we've distributed the A through. Okay? And in fact, that's exactly the way this works. And so we want to try to prove this. This is going to take a while, right? Because we have to prove that two sets are equal to each other. The left side and the right side are equal to each other. And this will take a while. So to make sure that we don't lose our way here, let's write this out in logic symbols so that we know exactly what we're doing. We have to prove that x is contained in the left-hand side if and only if x is contained in the right-hand side. So again, this is two parts. We'll have to show that the left-hand side is contained in the right-hand side. We'll have to show that the right-hand side is contained in the left-hand side. So there'll be two pieces to this proof. And inside those pieces, there'll be some pieces. So as you watch through this next part of the video, feel free to stop and rewind. And maybe as you do proofs like this in your homework, indenting, right, or setting things off in brackets, as you are working through your scratch work, can help a lot to make sure that you realize which part I'm still working on. So here we go. Let's pick an X in the left hand side. A intersect parentheses B union C. And what we have to do is prove that it's in the right hand side. Okay, well, what do I know about X being in the intersection of A with this parentheses B union C thing? Well, I know what intersection means because I go back to the definition. That's really all I've got to work with now are definitions. I know what the definition of intersection means. It means that X is in the first set, A, and X is also in the second set, that parentheses thing, B union C, whatever that means. Okay, great. I look around on the right hand side and I'm not really sure where to go with that. So let's just keep working with what I've got. What do I know about X being contained in the green B union C? Right? Well, back to definitions again. I know what union means. If X is contained in that green B union C, that means X is contained in B or X is contained in C. Right? Now we see we have cases. Right? X is in B or X is in C. So we're going to do each case separately. Right? So let's suppose that the X were in B. Okay? So now what I'm assuming is that X is in A, and now I'm assuming that X is in B. So great. If X is in B, and I already knew X was in A because that was, up at the very first line of the proof, then X has to be in the intersection of A and B because that's what the intersection means, right? It's in both sets. So if X is in A intersect B, right, then if I union A intersect B with A intersect C, whatever that is, that's a bigger set. So X will certainly be contained in that union because it's in the first A intersect B. You follow that? If you didn't, then that's why we have videos, so we can pause and stare at it. But remember that last line, it says consequently A is contained in A intersect B union A intersect C. In order to be in the union, I only have to be in one or the other. I either have to be in A intersect B or I have to be in the A intersect C. And in this case, we've proven that X is in A intersect B, so we're good to go. Now, of course, there's another case. We could have X inside of C instead. Well, you see exactly the same thing happens. If X is in C and we already knew X was in A, X has to be in A intersect C. So instead of being in the first half of that last line there, instead of being in A intersect B like we had on the previous screen, now X is contained in A intersect C. So clearly it's contained in the union of A intersect C with whatever else. So anything in the left hand side, A intersect parentheses B union Z. Anything in the left hand side, now we've shown has to be contained in an element of the right hand side. It took two cases to do it, but we're halfway done. We've shown that the left hand side is a subset of the right hand side. Right? That's half of what we have to prove to show that two sets are equal. Now, to prove that these sets really are equal, we have to go the other direction. We have to show that the left hand side, we've shown the left hand side is a subset of the right hand side. Now you have to do it the other way around. Show the right hand side is a subset of the left hand side. Whew. All right, let's wipe the screen and start over. So in order to do this, I'm going to say draw a line, let's start over, right? Another part of the proof. Next, right? Starting over. Now let's pick an X which is in the right hand side. This will be a different X than what we were doing a few minutes ago because this is part 2 of the proof. We pick an X in the right hand side. Well, that's something union something else. We go back to the definition. What does a union mean? It means I'm in one thing or the other. So X has to be in A intersect B, or X has to be in A intersect B or in A intersect C. Okay, one or the other. Oh, there's an or. Okay, that means we've got two cases again. X is in A intersect B or X is in A intersect C. So we do this with two cases now. First off, we say, okay, let's suppose that it was in the A intersect B, the one I wrote first. Okay, then if X is in A intersect B, then the definition of intersection means X has to be in A and it has to be in B. Well, since X is in B, it's in B union C because when I take the union of B with something bigger or different or whatever, X will still be in there. So if X is in B, X is in the green B union C. It's also in A, so it has to be in the intersection of the two. And lo and behold, that's the left-hand side of the equation. Second case works exactly the same way, only we replace all the b's and c's around. So if we suppose that x is in second case a intersect c, then x will be in a and it'll also be in c. Well, since it's in c, it's in b union c. So if it's in a and in b union c, it's in the intersection of the two, which of course that's the left hand side. So we get that the left hand side is contained in the right hand side. We've already done the other way, so the two sets are equal. Now, this was a long, complicated sort of proof, and this is typical of the kind of thing that we'll go through. But what should we do here when we're working out these kinds of proofs? Be careful to remember your definitions. When you see A intersect B, what does that mean? That means it's in this one and that one. Or B union C, that means that it's in this one or that one. And write out what all that means using the logic symbols. Being very careful to go through this and think about proof by cases and realizing that we had a proof by case inside of a proof by case in this example. That's very common. Okay? So what you'll also want to be very careful to do is to work out this proof on scratch paper. And because what I've written up nicely here looks nicely well written, and it all flows. When you do this the first time, it'll be a mess. I'm writing this and I'm writing that, and I'm saying, remember, always write out your scratch work, then rewrite it nicely when you turn it in, so that it looks like we've done on the screen, where there's no false leads and chasing our tail around and going down the rabbit hole that didn't work. Right? We figure all that out on the scratch paper and then we rewrite it nicely.